Hello. Thanks so much for coming on to this presentation. So what we're going to be talking about today here at the Sigmafine Summit is the benefits of combining advanced analytics and reconciled data. So this is going to be a case study that involves incorporating our software, Plantweb Optics Analytics, which I'll talk about more in a second, with Sigmafine in order to get better results than each of the software on its own. So just a brief introduction of who we are. So my name is Michael Torzidlo. I'm the product manager for a piece of software here that we have at Emerson called Plantweb Optics Analytics. And we'll talk about that throughout this presentation. And I'm joined today by Fida Jalasi. Hi, Fida.
Hi, Michael. So Fida Jalasi, I'm senior system integrator and team lead at automation at Emerson Automation Solutions.
All right. Okay. Thanks, Fida. So now let's get into the presentation. So here's the agenda for today. The things we're going to talk about really include who is Emerson. If you're not familiar with Emerson, give you an idea of who we are overall. What is optics analytics? So an introduction to our platform. And then Fida will be taking us through a case study of combining optics analytics and Sigmafine. And that is all around a furnace. So although it is a furnace case study, this is something that's very extensible as well. And then we'll just open up for questions and have a wrap up at the very end. So who is Emerson? So this is our 2020 at a glance. So Emerson is a global company that has two main platforms, automation solutions and commercial residential solutions. And we are coming to you from the Emerson Automation Solutions side. We were founded in 1890, have over 80,000 employees, and almost 17 billion in sales in 2020. And as part of that, Emerson Automation Solutions has about $11.2 billion in sales. So we have a lot of different products that you're probably used to and maybe use every day. So things like the Delta V control system, Rosemount sensors, Fisher valves, and so on and so forth. So that's where we're coming from today. And we're both involved in the digital transformation at Emerson as well. And one thing that Emerson does have is a partnership with Sigmafine. So this was announced a few years ago that in order to really ensure the highest accuracy and confidence in your measurement systems, that Emerson partnered with PIMSoft and Sigmafine to really provide that enterprise-wide platform to help customers validate accuracy, reliability, and usability of plant measurements. And as part of this, it's super important to have accurate mass balance and yield accounting data. And part of those reasons are to mitigate financial risk, reduce losses, and really just have better overall operations. So as a key part of digital transformation, this combination really helps lay the foundation for assessing, predicting, modeling, optimizing operations. So originally, this partnership was mostly around measurement validation, but as you can see in this presentation, we really extended that to different use cases. So this is our Plantweb Optics platform. So as part of Emerson Automation Solutions, we have software known as Plantweb Optics, and the real goal there is to help operations reach top quartile in areas such as reliability, production, manufacturing agility, sustainability, and health and safety. And the way that we do that is taking data from all around a plant, from machinery health to instrument and valve health to data that you might have in a historian. And our software helps turn that into measurable results. So part of that value proposition is really connecting, collecting, contextualizing data in our data lake, visualizing and analyzing that data, and really driving collaboration and workflow. So as part of this, we have a variety of different pieces of software, including data lake, portal, our connectors. So our connectors connect to Emerson sources and some open source standards. And then Plantweb Optics Analytics here, which really provides that advanced analytics capability, including machine learning and root cause analysis. And as part of that software, Plantweb Optics Analytics, we did win an award here, the 2021 IoT Breakthrough Award as the Analytics Platform of the Year. So here we were recognized for really helping our customers improve key performance areas like reliability, safety, production optimization, and energy management. So really proud of getting that award out of all of the nominations worldwide. And these are the main components of Plantweb Optics Analytics. There are two main pieces of software, Modeling Studio and Project Studio. And Modeling Studio is really about taking raw data and turning that into predictive models. So that can be cleaning, exploring, running advanced kind of analytics like clustering, classification, and finding more about your processes and your data that way. Then we have a few key modules within our Project Studio. One is our rules and complex events. That's really about detection of events in your software. And that's about setting logic in place to recognize things like, for example, column flooding. And then root cause analysis works in tandem with that. So that's really about putting together fault trees and automating root cause analysis to find the root cause of these events. So an event happens like column flooding, being able to figure out what event precipitated that is causing that flooding. Finally, you want to see some workflow. And workflow is all about really setting alerts and things like that. And it can be used quite broadly to automate parallel or sequential sets of operations. So an example here is if you have an event like column flooding, you find out the root cause of that event and you send out an alert or notification to operations about that. And then we all have, we see here the main components of Sigmafine. So things like modeling and reconciliation, tracking, identifying errors, and making sure that your KPIs are accurate. So with those two things together, what we wanted to do was combine those and see how they were greater as a whole rather than the sum of their parts. And these are what each of these bring to the table. So in optics analytics, we have things like KPIs for your assets and processes, root cause analysis and workflow. And Sigmafine really brings that data validation and some capabilities like mass and energy balance in. And combined, optics analytics and Sigmafine really provide an analytical platform that can drive action based on reliable data. As we know, data is necessary for analytics, and more so than that, reliable, good data is a part of that as well. So as we were working with Sigmafine, we came up with the idea to run a test of combining our two softwares. And this is a furnace case study around that. And Fida will kind of walk you through what we did in this case study. And hopefully you can get some ideas about how you could do something similar in your processes.
Thanks, Michael. In this part, I will go through a use case example around the furnace. In analytics, we use template and models to supervise and manage the performance of critical assets. In this use case, we worked on a fire heater. We made a model for it, which embeds years of expertise and process knowledge to preemptively alert operators about possible problems and prevent costly shutdowns. This model embedded performance calculations too, to identify performance target and recurrent problems and the root cause analysis to help find and mitigate the impact of deviations. As part of the model, we identified root causes for abnormal asset behavior. Also, we identified their impact on the equipment, environment, and business. The detection of the abnormal behavior is mainly based on the raw data. There is some challenges with the raw data that could be divided into two categories. The first one is with the measurement error. The measured data may be lost, contaminated by gross error, or distributed by random signals during the measurement process. So the final data displayed to the end user might deviate from the original data, which might affect the decision making. The second challenge is the lack of data. Sometimes we don't have enough instruments to generate the right KPI in the model. which might be caused by missing instruments on the field and that need to be compensated by estimation or process modeling. These two challenges may lead to make wrong decisions. The solution is to generate trustable data for the analysis through data reconciliation. This will bring considerable benefits like data correction, easier detection of measurement problem, and make effective decisions. We partnered with Sigmafine because it increases confidence of what we measure and estimates what we don't measure, which helps us to make better business decisions. This is what we get when we integrate Sigmafine with our model. Now, the raw data is flowing through Sigmafine and then fed into Optics Analytics model, which will deliver enhanced results, enabling the user to identify deviation from optimal mass balance, identify the cause of underperformance, and work toward corrective actions. So to start building the combined solution, we follow these steps. The first one is to create the model in Sigmafine. We start by building the furnace model, reconcile the data, and then estimate and measure it parameters. So Sigmafine uses the data reconciliation method, which uses a least squares formulation to quantify the error in the model measurements. Here we developed the furnace model in Sigmafine, which is empowered by thermodynamics extension to do the hourly integrated mass and energy balance of the furnace. Basically, we are reading the raw data from the Pi data archive. The data were structured in operational asset with Pi asset framework. After that, these assets are related together in a model and reconciled with Sigmafine server. So this is the Sigmafine furnace model. Each asset is represented by a standard Sigmafine template, which is represented in a modular display. Now we will do the data mapping and integration between Sigmafine and Optics Analytics. Once we have generated the reconciled data, we identified the data we need from Sigmafine in the analytics model. And we mapped these data to the KPIs that we need to generate in analytics. Then, in order to integrate the two components, Sigmafine generated the reconciled data and published it to the Pi server. Then analytics connects to the Pi server and read the reconciled data from there to generate KPIs. The combined model is fed by real-time infrastructure with process data and where required with laboratory data. It provides seamless integration with the customer infrastructure, able to interfacing with disparate data sources and data repositories, such as historian, ERPs, and business intelligence tools. So Sigmafine can either publish the reconciled data to SQL Server or Pi Data Archive server. The connection from analytics to the SQL Server is very easy and simple. For the connection to the Pi server, we need to install and configure PyBridge to connect to Pi server. Once connected, the Pi variables will be transferred to analytics as global variables. Now we will create the model in analytics. We started by adding a class. This class will embed calculations to calculate the asset performance. This template determines KPIs and metrics. Then it compares the calculation to a baseline or design values to determine deviations in order to identify potential instrument problem, pinpoint degradation source, and evaluate the effectiveness of cost improvement actions. The asset includes a set of properties where each property is assigned to a tag from Sigmafine for the reconciled data or from Pi for the raw data. Now we will go to the KPIs development. We use the custom K rules to compute KPIs like efficiency and heat duty. As you can see, This model uses a graphical environment based on drag, drop, and connect. After generating KPIs, we compared the calculation to a baseline or design to determine deviations and generate events accordingly. So the event here is generated when a low thermal efficiency is detected. Then we build a complex event graphical rule to determine root cause of the deviation. We used KRCA model in analytics, which allow creating fault propagation models that are defined by the cause and effect relationship. The possible causes of an abnormal condition are located upstream, and the effects are located downstream. For example, we detected a low thermal efficiency. The cause of this symptom is the instrument bad measurement. And behind this problem box, there is a logic that we define to trigger this problem when it occurs, like we saw previously. So this model provides also actionable knowledge for immediate resolution of performance gaps. These actions was associated with problem box and displayed in dashboards. For example, a message will be displayed to check the instrument FIT 101. Moreover, using Sigmafine data, we can determine which instrument is causing the issue and which measurement are contributing most to the imbalance. In this way, the root cause analysis based on reconciled data can serve several purposes. First, it acts as an early warning system for instrument malfunctioning or drifting out of calibration. And second, it acts as an online validation process where the performance of individual instruments can be compared for consistency against the rest of the measurement in the system. We can have more details about the low furnace performance by going into this icon. The low furnace efficiency symptom is associated with the bad measurement provided by instrument FIT 101. So this is the summary overview with drill down capabilities. We were able to estimate the unmeasured data like flue gas to stack and the vaporized crude. And then we were able to calculate the KPIs based on raw data and reconciled data. Then with the root cause analysis based on reconciled value, we identified which instrument has potential problem and generated actions for immediate resolution of performance gaps. This graph is a comparison between thermal efficiency calculations based on raw and reconciled data. As you can see, the efficiency is lower than expected. This bias between the performance indicators with reconciled and raw data is caused by bad measurements. The raw data set you can see on the left is used to study the correlation between the measured oxygen in the flue gases and the furnace efficiency. As you can see, the raw data set show a very poor correlation because of the inaccuracy of the measured data. So we used Sigmafine to perform data conditioning step based on mass and energy conservation principle, resulting in reducing the inaccuracy of the oxygen measured and making the resultant dataset suitable for use by optics analytics model. So the expected correlation appears. The use of the reconciled data, which are free of gross error and which satisfy all plant material and energy balance, enhance dramatically the accuracy of process model used for optimization, since larger gross error can nullify gains achievable through process optimization. So this is the impact of lowering target oxygen in the flue gas by 1% through analysis of reconciled data vs unreconciled data, which would result in improved efficiency of the furnace and an energy saving worth between 100 and 200 K per year, depending on the natural gas cost. Lowering the target oxygen in the flue gas by 1% will also lower nitrogen oxide emissions by 10 to 15%, allowing the refinery to more easily reach emissions target or allowance. Let's go now to the demo, and let's start with the furnace model in Sigmafine. The best way to visualize this model is to use the modeler or the Sigmafine modeler add-in to process book. As you can see, each asset is associated with an element template, and assets are related together in the model and reconciled. The reconciled data is then archived in the Pi server. This is the Pi system management tool that we can use to visualize the current value in the Pi data archive of the reconciled data from Sigmafine. This data will feed then our analytics model. This is the optics analytics project on modern runtime. We can check the connection status with the data sources, in that case with the Pi data archive through the Pi bridge. From the object watcher, we can check the variable status and values in the system. This asset is a user-defined template, which has properties, and each property is associated with a variable that we are reading from the Pi server. After defining the model properties, we calculate the KPIs like the efficiency and the heat duty. We used for that the K rules, which has a rich toolbox including arithmetic, statistic, temporal reasoning, and logic blocks that can be combined all in one rule. For example, this block is used to read the fuel gas flow from the furnace model. And this one is used to do an arithmetic operation. After calculating the KPI like the efficiency, we compare its value to baseline or design value to determine deviation and generate events accordingly. So let's take this example. Whenever there is a low thermal efficiency, an event will be generated. To summarize now, the K-rules model was used to calculate KPIs like the efficiency and trigger events if any deviation are detected. In the same way, we have developed other logic to detect a bad measurement in the process based on the reconciled data, which might affect the thermal efficiency values. So whenever there is an issue in the measurement, an event will be triggered and communicated to the KRCA trees in which root causes are identified. So each one of these problem blocks is associated with an event. We can show here the related events to the bad measurement, for example. To have more details about the problem, we can go to this icon and click on Show Tree View. So as you can see, the low thermal efficiency, the low furnace thermal efficiency is caused by bad measurement in the instrument FIT 101. Actions associated with the problem can be shown in the message browser as well. That was the demo for the combined solution. Back to you, Michael.
All right. Thank you so much, Vida. So as you see, there is some definite value and also some ease of use in combining optics, analytics, and Sigmafine. But when you show just one use case, but these are really the main use cases that you get from combining these two technologies of analytics and something like Sigmafine. So really just knowing that you have trusted data. Here you have the plant data. We take in information in our server, but that layer in between really can do things like data conditioning. It opens up a world of new use cases like custody transfer or reporting. And really looking to take what you've learned from analytics and drive action. So being able to have a visualization and a dashboard that quickly shows what you can see from a reconciled perspective versus a non-reconciled perspective, having root cause analysis, actionable advice that can really take your learnings and make sure that operations can do something about it. And here, really, what we're super interested in is how to improve sustainability, leveraging something like Sigmafine to really optimize processes, reduce energy emissions, and eliminate losses as we all look to become more sustainable. For more information about Plantweb Optics Analytics, you can just visit emerson.com/plantwebopticsanalytics, or reach out to your local Emerson representative or impact partner. And there on the website, you can connect with sales if you have any more questions. And speaking of questions, we'll now be opening up for any questions.